Now we resume our session, and our next speaker is Sushant Kala, and his title is Lower Bound on Height and Low Lying Zeros.
So first of all, I would like to wish a very happy birthday to Professor Balu, and thanks to organizer for giving this opportunity to speak on this occasion. So I'll be talking about lower bound on height and low lying zero of Dedekind function. So let's start with what is a height function. So height functions play a very important role in algebraic number theory and Diophantine geometry to give some kind of notion of partial order or size on some number theoretic objects. So give some kind of partial ordering so that we can talk about size, and it helps us to count objects. And the other thing, in some sense, it measures the arithmetic complexity of our object. So a very first example of height can be seen as the naive height function on rational number. So pk rational number in Q, where P and Q are written in the lowest form, and we can define its height to be the max of modulus of P and modulus of Q. So if you see clearly, so this function has some nice property. So if you pick some real number m greater than 0 and say how many irrational numbers are there whose height is bounded by m, so that will turns out to be finite. So this is called the finiteness property of height, and it plays a crucial roles in many instances. So if you see clearly, so if I consider the height of this rational number, so it turns out to be 2, and if you see this number, so these two number, if you see in the real line, they lies very close to each other, but if you see their height, so one object is very complicated than other. So that's how in some sense like that object is more complicated than this one. So the classical heights known as the Weil height also was defined by Andre Weil. So we are going to define Weil height on the algebraic number. So it's a non-negative function which is defined as, so pk number alpha belong to Q bar, and consider a number field such that alpha is contained in K. Then the Weil height is defined as, so we will sum up over all the places of K and consider this log max of, so where this is the absolute value of alpha with respect to this place nu. Okay. So this absolute value is normalized in the sense that this, our definition of height doesn't depend on this K, which number field I am taking, where alpha belong. So we can always take it to be K alpha. So now there is an equivalent notion of height in terms of Mahler measure. So Mahler measure for alpha in Q bar. So whenever I am defining height, I am always considering the non-zero number. Okay. So we pick alpha in Q bar and consider m alpha x to be its minimal polynomial in Zx. So its Mahler measure is defined as this modulus of an and product of So here this an is the leading coefficient of m alpha x, and these alpha i's are the conjugates of alpha in complex numbers. Okay. So in some sense the Mahler measure is measuring like how many zeros are lying outside the unit circle, Okay, and there is a nice connection between Mahler measure of alpha and height of alpha, and that is given by, so we have, so let's call nk the degree of alpha. So this degree times alpha is given as log of m alpha. Okay, so if you closely see the definition of Mahler measure, so we have this following thing. So Mahler measure of any number is always greater than 1, greater than equal to 1. And the second thing, so the second thing follow from a well-known theorem of Kronecker, which says that the Mahler measure of alpha is 1 if and only if alpha is a root of unity. This is the notation I will use for the roots of unity in Q bar, and this is equivalent to say that height of alpha is 0 if and only if alpha is a root of unity. Okay. So once we have this setup, so Lehmer asks this question. So we know that, okay, so m of alpha is 1 whenever alpha is a root of unity, but he asks, can we get algebraic number whose height is whose Mahler measure is very close to 1? And after some computation, he made this conjecture, which is known as Lehmer's conjecture. Which state that, so there exists an epsilon greater than 0 such that the Mahler measure of alpha is always greater than 1 plus epsilon for all alpha belong to Q bar, not root of unity. And in terms of height function, this conjecture can be stated as height of alpha is greater than C by nk, where nk is the degree of alpha, for some C greater than 0. Okay. So if you see the definition of Weil height and see the height of these algebraic numbers, so it will turns out to be log 2 by n, and n is the degree of this number. So it somehow says that, okay, so this right hand side, this 1 by nk cannot be made much more better. Okay, so this thing is there. So this conjecture is still open, and there has been a lot of progress in this direction, and Lehmer conjecture is proved for many interesting subsets of Q bar. So some of the results are following. So the first result is due to Smith in 1971, where he proved Lehmer's conjecture for non-reciprocal numbers. So by non-reciprocal I means alpha is not conjugate to 1 by alpha. Okay. And the second result is due to Singel in 1973, where he proved Lehmer conjecture for all the totally real number or CM number. So CM, I mean, so alpha is called CM if Q alpha is the quadratic extension of a totally real field, and totally real means all the conjugates are real. Okay. So using some complex analytic ideas, Singel proved Lehmer conjecture for this family, and later in 1999, Amoroso and Sinu David, they proved Lehmer conjecture for all alpha such that Q of alpha over Q is Galois. In fact, their result is much stronger. So their result hold for any alpha such that the Galois closure of Q alpha, degree of Galois closure of Q alpha has polynomial growth in terms of degree of alpha. So for those numbers, they have Lehmer's conjecture. And the recent result, and which is the major breakthrough in the 2007, and it's due to Dobrowski and Brouin and Mishgonif. So they have proved Lehmer's conjecture for this family of alpha, where the minimal polynomial m alpha of x, it doesn't have any cyclotomic factor, and all the coefficients are odd. So they use some kind of auxiliary function to get this result, and this is in Annals of Math in 2007. So these are some of the major results in this direction, although there are many others. But due to time constraint, I will not go into that. So in this direction, we have proved some kind of lower bound for height, which gives us Lehmer's conjecture conditionally for a certain class of algebraic numbers. So for that, I need to define a few things. So let k be a number field, as we have seen in Dhananjay's talk. So let zeta k be the oh, this one? Okay, so if m alpha x has no cyclotomic factor and all the coefficients are odd. So for those alpha, they got Lehmer. Yeah. Okay, so zeta k is the Dedekind zeta function. So let's define nk of t to be the set of all zeros of zeta ks in the box. Sigma is between 0 to 1 and t. So basically, we are looking at zeros in this box. Okay. Then we define some kind of summation supported on the zeros, this set nkt. So let's call it zk. So let me write it here. So this is the following summation supported on the zeros up to height 2. So as I take my height to be smaller, so these zeros are like very close to the real line. So that's why we call them the low lying zeros. So we are seeing this summation over all the roots of height at most up to 2. So then in our recent work, this is one of the result that we obtained. So let me write it here. So this is a joint work with my advisor Anup Dixit. So for alpha belong to q bar and k is equal to q alpha, under GRH we have that this height of alpha times degree is bounded below by this quantity zk by nk minus log degree plus some error term, which is absolute constant, means it doesn't depend on which alpha I am choosing. So we have an explicit bound for this big of 1. So as a corollary of this result, we get that. So under GRH for alpha in q bar such that this zk is greater than nk log nk. So for these type of number, Lehmer conjecture hold. And this can be seen immediately from this theorem. So how much time I have? Okay, yeah. Okay, so I will end my talk with few remarks. So the idea of the proof goes via Mahler's inequality and some computation with the explicit formula. And one of the thing is that, so from the Mahler's inequality, if we have our discriminant is say greater than nk log nk, so for that Lehmer's conjecture hold trivially. So the question is whether this theorem gives you Lehmer for the numbers for which you have log discriminant less than nk log nk. And some computation shows that, so we have examples where log dk is less than nk log nk, but zk is greater than nk log nk. So we got some enough number of examples up to degree 10. So hope this is true for many algebraic numbers. So yeah, that's all I want to say. Thank you.
Anyone has any questions?
Yeah, so those we have computed on Sage. So yeah. Yeah. Yeah, so that was like the height of the lowest zero. Yeah, so that was kind of motivated by this. So if we have the smallest zero very close to half, then we can expect the enough number of zero up to height 2. Yeah. Yeah, so only the degree is there. Okay, so the thing is that so when we have alpha to be non-integer, like not algebraic integer, then we trivially have that because so as there we will have the leading term of the minimal polynomial is 2. So for alpha non-integer, the Lehmer conjecture is always true. Okay. Yeah. Yeah, yeah, it will be independent. Yeah. Yeah, so actually, so there will be some factor involved there. Yeah, so that we can control. So like, okay, so this theorem, okay, so there is something. So this thing holds for if we consider algebraic integer. Okay, so if we don't have algebraic integer, so like it follows via like consider the minimal polynomial, consider its discriminant, and then it relate it to with the discriminant of the number field. So there will be some index factor going on in between. So that will involve there, like if we consider the different generator. Yeah. Yeah.
Any other questions? If not, then let's thank our speaker.
Okay, thank you.